Alright, in this video I'm going to sort of go through and dissect the time-dependent Schrodinger equation, but the first thing I wanted to do was give sort of a shout out to this book here, which is, as I go through the Schrodinger equation, I'm somewhat following this book here. It's A Student's Guide to the Schrodinger Equations by Daniel A. Fleisch. And there are several students' guide to physics books, and they're somewhat hit or miss. I've looked through the ones on Maxwell's equations, on classical mechanics, and on general relativity, and I found that they're by different authors, but I found this author, Daniel A. Fleisch, who also did the Maxwell's Equations Student's Guide. I think he does a really good job. Some of the other ones, like I said, the classical mechanics and the general relativity students' guides, I didn't think were all that great. But the ones by Daniel Fleisch are really good. So the Schrodinger equation one and the Maxwell's equation one, which are the two by this author that I've looked through before. So if you are interested in learning more about Schrodinger equation or sort of studying it on your own, or the Maxwell equations, if you're interested in that, then look for the student's guide to those. And yeah, so anyway, I thought this was a good place to make a shout out to this book, since I'm actually going to just be using a couple of the figures from this book in this video today. So without further ado, we'll get into this. So this right here is the time-dependent Schrodinger equation. So one of the ways you can see it's time-dependent is it has this right here. So this is the derivative of the wave function with respect to time, and we see here that we have the set that set equal to, so this right here is just sort of a constant. Same with this right here, and I'll get into what those terms mean, but for right now we'll just say that it's so we have the first order differential with respect to time, and is equal to some constant multiplied by the second order with respect to space, x here representing space. So we see that this is one-dimensional because we're just using one dimension of space. You may have seen this written such that it's using this del operator here with the wave function here, and this just means that we're using three dimensions. So it would be the partial, and so this would actually be the second. So it would be the partial with respect to x plus the partial with respect to y plus the partial with respect to z. It should be that, and these should have that. So you might see it having been written something like this, but for simplicity, and we'll get into the three-dimensional, we'll get into three dimensions of this in later videos, but for now we're just, for sort of simplicity, using just one dimension of space. And so if we want to sort of dissect this, and obviously we also have the potential here, and I'll get into that later on in the video. So to dissect this, the first thing we'll take a look at is this first order differential with respect to time. And so this is telling us, that, well, I guess we can first sort of back up even a little bit further and say that this right here, this psi, or psi, as you might have heard somebody pronounce it before. So this psi here has units, essentially of probability. Well, this is, it would actually be psi squared, or psi multiplied by the complex conjugate of psi is probability uh, at a certain place in space. And so, um, I mean, you'll see it a lot of times as m, which is for meters. So we might say probability per place is meters. For this, since we also have an m here for mass, I'll just write distance. So probability in space or distance or whatever you want to call it is probability in spatial dimensions. And so this is the probability in spatial dimensions. So it's the probability at some place in space. Or at least, like I said, if we take the Born rule here, that gives us the probability in space. And so from that, we know that if we take the differential with respect to time, what we actually end up with. So this right here, without squaring it, would have units of 1 over the square root of, and this is where it gets kind of confusing. So a lot of times you'll see it as m for meters. I think I'm just going to do d for distance, or you could use s for space, but then we get into the problem that we also use s for seconds. So I'm just going to use d for distance here. You will often see this as 1 over the square root of meters because that is the unit of space. But just to keep it simple, because we have this m for mass here, I'm going to use the square root of d for distance. And then if we take the derivative of this with respect to time, we end up with units of seconds, 1 over seconds times distance, like this. And so, like I said, this is just telling us the change in this probability amplitude with respect to time at a given location. So we're not looking at different places and locations. If we have some space here and we want to look at the change in the probability at that location there with time. So the probability is going to change at that location over time. And so that's what this is telling us right here. And then if we want to look at this I, so we know that I is for the imaginary number, and that is equal to the square root of -1. So this essentially is just telling us that the solutions to this are going to oscillate. They're going to be waves. So we know that from our Euler formula that if we have e to the I, and I will sort of suggestively use t here for the variable, that this is equal to, and this time I actually wrote it down so I know it's cosine plus I sine of x. I don't remember, but I may have written it with the sine and cosine switcher on, but I've written it down this time, and so that should actually be sine of t plus I sine of t, since I used t up here. And so we know that this gives us something that is a wave solution. And you can tell that that works because if we have, say, for instance, I, h bar, and then we have our partial with respect to time, and we are taking this with this, then if we take this partial with respect to time, what we actually get is I squared, because that I comes down when we take the derivative h bar e to the I t, because because e to something, the derivative of that is just, or e to the x, the derivative of e to the x with respect to x is just e to the x. And we know that this here is just -1, so that is just negative h bar e to the I t here. And so we know that that this I is just giving us solutions that will be waves here, and that is an important thing, which I will discuss in a little bit here. But first, if we continue our dissection, we see that we also have h bar. So I just talked about I here. I talked about this right here, this change in the probability amplitude with respect to time, and now h bar, which is the modified Planck constant, and that is equal to the Planck constant divided by 2 pi. And so the Planck constant is just telling us that that we're working with energy here, essentially. So the Planck constant is just the conversion between energy and frequency. So h is going to be equal to energy over frequency, and this is a constant, so that tells us that if there's a change in this, there has to be a corresponding change in this, and vice versa. So we know that that E and that energy and frequency are related to each other using this Planck's constant here. And so when we use this version of it, we are just changing it to angular frequency. So now we have, and I've been using nu. You will often also see this using omega, this lowercase omega for there, but I've been using nu, so I will stick with that. So this gives us the angular frequency. And we also know that that with this we can also relate it to momentum. So momentum is the modified Planck's constant multiplied by this this wave number here. And we know that the wave number is in units of 1 over distance. So I'll write distance here. Like I said, you will often see that as m for meters. That's the units of distance we're using, but to try to avoid confusion with the mass here, I'm just writing in distance. And we also know that given these relations, that we could write energy as being the momentum squared over 2m. And this is the same as h bar squared k squared, or wave number squared, over 2m. Since we know that momentum is equal to h bar k, then momentum squared must be h bar squared k squared. And like I said, this right here is the mass from it. And we saw earlier that we could use these relations to actually end up sort of quote-unquote deriving this time-dependent Schrodinger equation here. And this is just sort of a little, I guess, coda to this, is the units on Planck's constant. So h has units that are joule seconds, and this will turn into so kilogram meters squared over seconds squared. That's what joules are, and then we multiply that by seconds, which gives us kilogram meters squared over seconds. And we can see that this is the same as having joules per frequency, which, as I said up here, we have our energy over frequency. That's our energy joules over frequency. That's our H there. And we can see that this works because what this would be is we would have our kilogram meter squared over second squared. And this would be divided by 1 over seconds. And if you remember your sort of elementary algebra, if we divide by something that's already sort of a division here, that is the same as kilogram meters squared second squared times seconds. So if you're dividing by something that's already sort of a division, you just sort of flip it up and turn it into multiplication, and this right here gives us our joule seconds back. So we can see that that works when we have the joule over frequency here. That gives us our joule times seconds as units. So that's sort of where that kind of sort of weird joule times seconds comes from in the units on Planck's constant. But if we have the modified Planck's constant, then what we have essentially is joules over frequency radians. So this 2 pi just, or the 2 pi up here gives us radians, and radians are unitless, so it just still ends up being joules over frequency, except now we make it into angular frequency here. So anyway, that's sort of how the units work out on Planck's constant. And so the next thing to start dissecting, so we've talked about the h bar, which is the same as the h bar here. We're just squaring. Mass, I think is a little bit. I think everybody sort of understands mass in physics terms. Mass is just the sort of the resistance an object has to changes in its velocity or momentum. So if something has higher mass, it's going to resist when you try to push against it. Obviously, it's just going to resist that change in its velocity that you were trying to apply by pushing it. So that's just sort of the physics definition of mass. But now we can talk about this second order differential here of the wave function with respect to space. And so that, as I said, is the partial derivative of the wave function with respect to space, and that's the second order differential. And this is just the change in the wave function over space. And because it's the second order, that just tells us something about the shape of the wave function in space. And so to sort of better understand that, so if we take our Schrodinger equation here, which is the IH bar, and then draw that psi better, with respect to time is equal to negative h bar squared over 2m. And then we have our second partial of the wave function with respect to space. And then if we just do a little bit of sort of elementary algebra here, if we just divide both sides by IH bar, what we end up with is we have our first order partial with respect to time is equal to, so h bar squared divided by h bar is just 1 h bar. If we have an I in the denominator, we can switch that into the numerator. So I'll put the negative down by the I here and say we have 1 over negative I. We can just multiply that by I over I, which is 1. So this gives us negative 1, because I times I is negative 1. Then I times 1 is 1. And so this just gives us positive I. So what we can do is just move that positive. We just make it positive and move it into the numerator. So that's I h bar, because we're canceling out one of these h's here, over 2m, and then the second partial with respect to space here. Then what we see here is we have a first partial with respect to time equals some constant multiplied by the second partial with respect to space. And this is actually very similar to another equation, which is the first order of this function with respect to time. So this is just a wave function, so it's just a function equals d multiplied by the second order of that function, which is a function of space and time with respect to space. And this is actually the diffusion equation. So it's the diffusion of, say, heat in an environment. So if you have some room here and you apply heat to a space right here, we know that that heat will start diffusing throughout the room. And this tells us the rate at which that heat diffuses through the room. And this tells us sort of the shape of that heat. So you can imagine if you have heat here, it's going to diffuse in all 3 dimensions. And this tells us sort of how that heat looks in space as it diffuses over time. And it's the same equation for the diffusion. So if you have if we're looking down at a tank of water here and you sort of drop a little food coloring here, a little dye here, we know that that will start diffusing throughout this tank of water here. And this tells us sort of the rate at which that happens, and sort of the way that that will look in space in the water. And this d here is sort of well, it's a constant that's going to depend on say the liquid in your water tank, or the medium, whatever the gas is in the room in which you apply that heat, and so forth. So this is a diffusion equation. And so what you will notice, though, is that so this d here is a real number. It's not a complex number. What we have in the Schrodinger equation, though, is this I here, and that's where this makes sort of a big difference in this, is that the I makes it so that the solution to our wave isn't just that we have some wave here, and then over time it will just sort of diffuse out, then over more time it just sort of ends up flat, the way that diffusion happens. With the I there, we end up needing solutions that are waves, and so you will end up with a wave solution like this, which over time will just be another wave solution like this. We're not going to get this sort of diffusion outward over time, and that's what the I is doing in this situation. So these are the figures. I just took a picture of them with my phone here, and am using that. But these come from that book that I was talking about, this A Student's Guide to the Schrodinger Equation. And so what we see here, so this is talking about it in terms of the diffusion equation, and we see how that works here, where we have this is the sort of the in space, I guess you could say. So if we think of this as a one-dimensional sort of tank of water, so we have our tank of water that looks something like this, and we have, the water in here, and we apply the food dye right here. We can say that we're applying the food dye right here. So this is sort of the diffusion of the food dye. So you could imagine that so this says this is at time at t equals 0. We could imagine maybe at time t equals 0 that it would almost look more like a delta function like this. So maybe this, we could say, is a little bit further into the future, where the distribution of that dye has sort of spread out a little bit. And what this is telling us here is that when we have negative curvature, the slope is positive and getting less steep. So that's what that second order is doing here. That's what that is telling us here. So we're not looking at the curvature. We're telling us how the curvature is changing, and we see that the curvature is getting less steep here. So the steepness is sort of it's how much up it has for it. And we see that it's getting less and less up here. And the negative curvature here, the slope is negative and getting steeper. And so since the slope is negative, then getting steeper is sort of giving us the negative slope here. And then we have down here, after the inflection point, positive curvature, the slope is positive and getting steeper. The slope is negative, getting less steep. And so that just kind of goes back to our basic interpretation of calculus here. When we have a second order differential, then the slope is negative. That would be the first differential, but it's getting less steep, so that's the second differential, and that's why we care about the second differential. And so this tells us that that here, because we have positive curvature over here and over here, that this is actually moving upwards, as you can see here, whereas where we have negative curvature, it's moving downwards. And so that's telling us that we have this diffusion where it's at this highest part, it's going lower, and then at these lower parts, it's getting higher, which is how we end up getting this sort of over here. So if we go from some time here to some future time, we see that this part has gone down, and then on the sides here it's gone up. And then we move over and we end up with it just sort of being diffuse, evenly distributed throughout. And so that is the interpretation here of the diffusion equation. But like I was saying before, we have this I here, this imaginary number. So our solutions are going to be in the form of e to the I, and then our variable here, which, as I said, is the same as using our Euler formula, is the cosine and I sine, which tells us that those are wave solutions. And so that's why, as I said, if we have a wave function, we don't just see it sort of distribute out over all of space. We have we maintain our wave here, and so we'll get into that more in the future when we start solving the Schrodinger equation. But anyway, that is just what I wanted to show is is sort of maybe a somewhat helpful way to try to interpret the Schrodinger equation in terms of just thinking about it as similar to this diffusion equation. So I'm interjecting here because after finishing recording this video, I thought I didn't explain this connection between the diffusion equation, which I have written right here. So this is the diffusion equation, and the wave equation or the wave equation that is the Schrodinger equation, the Schrodinger equation. And so I pointed out that these have a similar form. They have this first differential with respect to time. They both have this second differential with respect to space, and they both have this coefficient here, where the difference here is that that with the Schrodinger equation it has this I in it, making it complex, where this is a real number and it's dependent on temperature and things like that. And so I pointed out that this tells us that the concentration at a given point x in some we can imagine in some container. So if we're looking down into a container here, we can think about, and we say we're measuring at this point right here, and we add some food dye right here, we know that it's going to start diffusing outward. And so we know that at this point the concentration, if we plotted the concentration over time, that at this point right here that we would see it at 0, and then it would start sort of going up and plateau here, where once the concentration of this dye has become evenly distributed throughout this container. And we could measure at whatever point we wanted to. That's arbitrary, but the idea here is that if we look at the concentration at that point, it's going to go up and then plateau, and this tells us how this is going to change over time. And so the concentration at a point x changes in time, where with this one, the probability amplitude, remember that it's a probability once we square it, or to be more precise, we multiply it by its complex conjugate. This gives us the probability. But if we have just the psi here, then it's the probability amplitude, which is a complex number, and therefore is a little bit more difficult to interpret, because with probability, probability has to equal 1 if you add all of it up, and it has to be positive. Where probability amplitude, you can actually, if you plotted it, you could actually have negative probability amplitude, but once you square this, then it will be something like that. But anyway, that's I talked more about that in a previous video. But the idea here that I wanted to sort of make a little bit more clear is this idea that the concentration at a point changes in time t, and that concentration. So if we say we start at a high concentration, then it's going to go down. If we start at a low concentration, it's going to go up until it meets that point there where it's evenly distributed. So if we go back here, we see that it's going up here where it's lower concentration, and down here where it's higher, until it reaches that point where it's evenly distributed. The difference with the Schrodinger equation, as I said, is because of this imaginary number here, which so instead of using the real number line, we're using the complex number plane, the complex plane, where here you could imagine that that if this right here would be sort of the equilibrium concentration. So this is the real number line, and we can imagine that the units for it are concentration. If we start here, we're going to go down here. If we start low, we're going to go up to this concentration, which is kind of what I represented over here, or what I represented up here. Whereas with the probability amplitude, if we're using this complex number, instead of sort of going up and plateauing up here and having it stop, what you will see is so this is the prob amplitude and this is time, is that you start here, then you'll go up, then it'll go back down, then it'll go back up and down. So this is the probability at a given place. And so if we say we have a container here, and we're looking at the probability amplitude right there for maybe some electron in this container, the probability would oscillate like this. And so instead of going down and converging at this point, essentially what it's doing is going around and then coming back around again and going around and around. And so you'd probably actually put the line right here because, like I said, it goes down into that negative, which would be when we're down here. And so you see here that we have this oscillation. So you could think about it like this. If we have a container here with water in it, say, and we add some food coloring right here, if we're using just this diffusion equation, then it diffuses out until it becomes evenly distributed. But if we add that I factor on it so that it becomes a complex number, you could imagine that that it would be more something like we start with it right here and then it diffuses out until it becomes well, strangely enough, as I said, we get this sort of negative probability amplitude. So instead of going out till it's evenly distributed, it actually goes out until it has some sort of weird negative distribution. And then after it reaches a sort of trough on that, then the diffusion goes back in reverse and everything collects back here in the middle, so that if we're looking at the concentration at this point here, we see, for instance, so we start with it at 0 and then the concentration goes up as this diffuses through and then kind of goes back down, and then we get that weird negative concentration, which is why it doesn't really translate well to this idea of concentration. But if you can just sort of use your imagination to imagine what negative concentration would be, and then back up here. So it's like it diffuses out, then sort of comes back so that it's 0, and then somehow sort of negative concentration, and then back to 0. And so that's what's happening here with this this factor of I on here, is that now instead of using this real number line, we're using this complex number plane. And so you get those oscillations rather than just sort of converging on a point where everything is evenly distributed. We are now just oscillating back and forth. So it would be like, as I said, it'd be like if our concentration was in this one point is oscillating from 0 up to some, I guess, evenly diffuse point, then back down to some weird negative concentration, then back up to having 0 concentration. But in this case, we're talking about probability amplitude, which, as I said, can have this this weird negative here, which is hard to interpret in any sort of physical way, which is why we use this Born rule here. By multiplying it together, we get all positive numbers, and that gives us the probability. So anyway, I hope that made this connection between the diffusion equation and the Schrodinger equation a little bit easier to understand. So I thought I'd just put this little interjection in here. And now back to the rest of the video. And so the last thing to sort of dissect out of this is this potential here. And so we can think of the Schrodinger equation as being the same as our energy here, which is energy is equal to kinetic energy plus potential energy. And so we can think of this right here as our energy and this as our kinetic energy here. So this is our kinetic energy right here, and then we have our potential, which is often just denoted as an uppercase V here. So you'll often see it written as E equals T plus V, where T is the kinetic energy and V is the potential energy. And so the potential can be a lot of different things. So probably what you will end up thinking about it sometimes in chemistry and quantum mechanics is the potential energy of the nucleus. So we have the nucleus, and then we have an electron here. So that's sort of the Bohr model, the classic model. Excuse me. But anyway, you could also think of it like this, and then we have our sort of our electron cloud around it, and it has this potential here. But we'll get into more of this in later videos. So one way to think about this, though, is, I mean, you can imagine that if we have E equals T plus V, that E is necessarily going to be greater than or equal to one of these. So E would have to be, if we have no kinetic energy, then E would be equal to the potential energy. But if there is kinetic energy, then it would have to be greater than the potential energy. But in quantum mechanics, the energy that we know is just the expectation value, which is just sort of the average energy. And so that's how we can actually get these places where if we have this potential here, so this box here is denoting a potential energy, and we can actually have energy being less than the potential energy, and this is where we get this quantum tunneling here. So if we have a particle here and it's inside some container, where that container is acting as a potential energy barrier, you can actually have the particle move out of that container. If the potential energy here is finite, we'll talk about later the so-called particle in a box, where we say that this potential energy is infinite, and so then we contain our particle inside the box. But when we have this strange sort of potential energy being greater than the energy, then we can get this quantum tunneling, which once again we'll talk about that more in future videos. But anyway, the potential energy is sort of this this thing that's I guess you could say it's putting boundaries, so boundary conditions perhaps on solutions to our wave function here. And so anyway, that, as I said, is a sort of dissection of the Schrodinger equation. I talked about this first order partial with respect to time is if we are looking at a given location in space, then we can think of it as sort of the change in the probability with the change in distance or the change in space or location uh, or whatever you want to call that. Well, no, it wouldn't be. Yeah, it's so the wave function is the probability at a given location. So that's what I meant here. So it's the probability at a given place in space, at a given location, distance, which, as I said, is in meters. And so when we take the derivative of this with respect to time, we are looking at it at the probability at a given location, at a fixed location. We're seeing how that changes in time. And so you could imagine, so if we say that we have waves as the solutions to our function here, then we might have a wave like this, and then at some later time it might be like this, sort of moved over. So if we're looking at this location in space, we see that that it changed from here to here. So this is our probability amplitude. It changed, the probability amplitude changed as some time passed. And then I talked about how this I is important because that tells us that our solutions are going to be waves and not just sort of a diffusion, so that the wave just sort of over time sort of spreads out. It's not going to be a solution like that. It's going to be a wave solution. I talked about the Planck's constant and how that is how we sort of relate the frequency to the energy, so that we know that higher frequencies are higher energies. And then we talked about this, which is just sort of the shape in space, and that was what brought us to these here, where this told us, so because it's a second order differential here, it's telling us that whether it has positive or negative curvature, which is giving us a shape like this. And then the change in time, so if we change in time, then we could see with the diffusion equation that we have this diffusion happening where this is sort of flattening out. So the change in time is going to be somewhat different in our Schrodinger equation because of that I here, that imaginary number here. And then the potential, as I said, over here is just telling us, so a potential is essentially sort of a barrier here. And so that's how we can think of the potential. So if we had the potential around a nucleus, then what you will often see, and I forget the name of the equation that gives this shape, but you will see a potential that looks sort of like this, and we will sit in this potential well here, where you need more energy to move outside of this this potential well here. So this over here would be where the nucleus is, and this is space getting further away from the nucleus. And so if you know your chemistry, you know you need to put energy in to sort of eject an electron off of an atom, and that's what this function right here is telling us, is the amount of energy that we would need to get our electron to go from here out to here away from the nucleus. And that's we'll get, like I said, we'll get more into potential energy and sort of what that means in later videos. But anyway, I hope this dissection of the Schrodinger equation was at least somewhat helpful for you. I think later videos will start having this make more and more sense, what all of these different things mean, especially once we start getting uh, into solutions for the Schrodinger equation, and we can start seeing uh, how that I makes it different from this diffusion equation, in that our solutions will be wave functions. Anyway, uh, yeah, like I said, I hope this video was helpful to you. Uh, if it still doesn't make a ton of sense, uh, like I've said before, it you know the thing that helps is just exposure. That's John von Neumann quote that nobody understands math, you just get used to it. That's very true in a way. You just have to keep exposing yourself to more and more of this. You can re-watch older videos of mine, or you can find other YouTube tutorials on this to get sort of different explanations. Like I said, you can check out the book, The Student's Guide to the Schrodinger Equation. Maybe if you watch my video and then read this, something will start clicking in your mind, and it will just start making more sense. So anyway, yeah, I hope to encourage you to just, if it still doesn't make a whole lot of sense, just kind of keep exposing yourself to these concepts and these ideas, and over time you'll just start getting used to it, and then you'll look at an equation like this and it will just sort of make sense to you. But anyway, I will see you in another video.